Hi, Mrs McTaggart here. In this video we're going to look at the higher differentiation, in particular the topic of stationary points. Now this is a nice bread and butter question in terms of it always comes up and it's always a nice 6 to 8 marks depending on how good you are at remembering the method. So stationary, if you think of the word stationary, not to do with the pens and pencils but to do with standing still. Stationary is when you are stopped. And in terms of maths, the stationary points are when a curve has a gradient of 0. They're called points of interest, or more particularly the term we use is turning points of our curve. So it's where your curve starts to change direction and go from up to going down. It creates a maximum turning point, for example. Now the method to determine stationary points are this bit down in yellow. So step 1 is we're always going to differentiate. Step 2 is you put your differentiated term next to 0, because remember f dashed x is really just your gradient. So you're saying that your gradient is 0 and finding the corresponding x value. Now that'll give you your x coordinate of your turning point. We sub that back into our original function or equation to get our y coordinate, and then we're going to do something new called a nature table. And the way I do my nature table might be slightly different to the way some of your teachers do, but I'll explain more of that when we get to it. So let's look at an example and we're going to work through these 4 steps. So we have to find the stationary points and their nature for this curve. Now a question will say it's looking for stationary points and it will mention they want the nature. So what we're looking for is we're looking for the coordinates where the graph starts to turn, and we're looking for whether they're maximum or minimums, or I'm going to teach you a new word here as well. So the first thing we do is we're going to differentiate f of x. So f dashed x will be, remember we're timesing by the power and lowering the power, so this is a simple bit. So this gives us 4x cubed minus 12x squared. Then we do a little sentence that says for stationary points, we are going to set f dashed x equals to 0. Now, if that isn't in terms of f dashed x, if that's y equals, then it becomes dy by dx instead of f dashed x. So for stationary points, we're going to set f dashed x equal to 0. Now this is a statement that you must write, okay, because it can sometimes get you an extra mark. And if you get into the habit of just always writing it, it's just reminding you what you're going to do. So we're now going to set this equal to 0. So we've got 4x cubed minus 12x squared equals 0. Now at this point we're trying to find what x is, so it could be solving a simple equation, it could be factorising, and remember factorising does involve common factor, difference of two squares and trinomials, okay? So be on the lookout for all of them. Now my example here has got a common factor of 4x squared. So I'm going to take 4x squared out, leaving me with x take away 3 equals 0. Then you put each of these equal to 0. Now, 4x squared equals 0 would mean that x squared was 0, and the square root of 0 is just x. So this gives us, I said that wrong, the square root of 0 is just 0. So x equals 0. And this one here gives us x equals 3. So they are the first parts of our coordinates. So I know I have a coordinate 0 something and 3 something. Now I need to get the other numbers, so what I'm going to do is I'm going to plug those numbers in and I'm going to get my y coordinates. So I'm going to do f of 0. So I'm going to place 0 back into the original. Remember, this is the original equation. Don't sub into the differentiated term or you'll just get 0 each time. You have to put it back into the original because the coordinate is from the original graph. So f of 0 there would just give me 0 take away 4 times 0. So which I hope you're all happy is 0. So your first turning point is at 0, 0, which is your origin. The second turning point would be when x is 3. So you've got 3 to the power 4, so that's 3, 9, 27, that's 81. Take away 4 times 3 cubed, so 4 times 27. So that is 81, take away 108. I can do this quickly because I've done it so many times. And that gives me 27. So my turning point is at 327. Then we're going to do this thing called a nature table. So your nature table looks a wee bit like this. And we have, on the first column, we have x, we have f dashed x, or dy by dx, depending on term, and then we have the bit called shape. Now, for the sake of this, I need to write down here what f dashed x was again. So I'm just going to remind myself that f dashed x was 4x cubed minus 12x squared, because as I work up my page I start to lose that. So my nature table. So what we do is in the top of your nature table, you put in the values you got for your turning points. So I got 0 and 3. So you put them in the table in numerical order. So you do 0 and 3. And what you do is you do an arrow up to the 0, an arrow after the 0, and an arrow after the 3. So I'm interested in the shape of this diagram before 0, between 0 and 3, and after 3. Now some of teachers will teach that and split it into 2 separate nature tables. I just do it in the one. Now f dash x is your gradient. This is going to help us decide whether our graph is increasing or decreasing. So we already know that the gradient at 0 and 3 was 0 because we set f dash x equal to 0 there. And if you plug these numbers back into f dash x, you'll come out with 0. So what we do now is we pick numbers before 0, after 0 and after 3. So I'm going to just pick my numbers first of all. So a number before 0, let's go with minus 1. Between 0 and 3, I'll just use 1 because that's a really easy number to sub in. And after 3, I will go with the number 4. And when I get to that, I might talk about a different option I can use. So what we do is into f dash x, we sub in each of these wee numbers. So you don't necessarily always have to do working for this one because I'm not looking out for an actual numerical answer. I am just looking to see if my graph is positive or negative, so I can decide if it's positive, then I know my graph is increasing, and if it's negative, I know it's decreasing. So if I was doing f dashed minus 1, well, I can't speak. Minus 1 cubed would be minus 1, so the first term would give me minus 4. Minus 1 squared is just 1 times 12 is 12, so I'd have minus 4 minus 12, that's negative 16, so we're going to put a wee negative in there. Pick the number between 0 and 1, so if I do f dashed of 1, then that just gives me 4 take away 12, which is also negative. And then if I pick a number bigger than 3, so if I plug in the number 4 here, well 4 cubed is 64, so I've got 4 times 64. Take away 12 times 16. So 4 times 64 is 232. 12 times 16 isn't quite as big as that because I know 12 12s are 144. So 200 and something take away 100 and something, it's positive. So I don't need the exact number. If you have a calculator, feel free to go do that and work it out. And then what we do is we fill in the shape bit. So the first bit of my graph is negative, so my curve is going down. Decreasing. When the gradient is 0, that means your graph is stationary. This is the bit your turning point. Between 0 and 3, it's negative again, so it's going down. That point is stationary, and then at the number 4, it's increasing. So we have this kind of shape here. So this first bit of the graph, it's 0, 0. When you have your graph going down along down, this is a new word for you. This is called a point of inflection. So that is point of inflection. And then this other turning point at 3 was your 327. And that's clearly got this kind of curved shape here, doesn't it? So we should know already that that is a minimum turning point. And I can't quite fit in minimum. And that would be a minimum turning point. And this is what they're looking for. This is the answer to the full question. You must have that. You must have both your coordinates written out in full and stating what the nature is. That is you've found the nature of those turning points. So that's my first example. Let's try another one. So similar to the previous one, we have to find the stationary points and their nature. And this curve is f of x again. Now this one isn't ready to differentiate, so we have to do a wee bit of prep work first. So if I expand this, I'm going to think of this as, if you need to, I know a lot of us can expand this without writing out x minus 6 all squared. This gives us, when you multiply this out, first terms give you x squared, the outsides give you minus 6, and the insides give you minus 6. So that is negative 12 altogether, x. And then the last two things give you plus 36. I'm then going to multiply that through by x, so I have x cubed minus 12x squared plus 36x. Right, now I'm ready to differentiate. So this was my basic term all expanded. So f dashed x equals times by the power lower the power gives you 3x squared. Take away 12 times 2 is 24x. And 36x when differentiated just goes to 36. And remember that wee bit that for stationary points, I'm just going to shorten it for SPs. We're going to set f dashed x equal to 0. So that's a wee statement that you have to write. Now if I put this equal to 0, it's going to be a trinomial that I'll need to factorise. To try and make my work a wee bit simpler just now, I'm going to take out a common factor of 3. And that will make it a basic trinomial. So that gives me x squared minus 8x plus 12. And I'm going to put that equal to 0. So from there, we can then put it into two brackets. We're looking for numbers that multiply to 12 and add to 8. They're both negatives, so I'm thinking it's a minus 2 and a minus 6. Both of them multiply to 12 and add to minus 8. So from there, when you solve that, you have x equals 2, x equals 6. So we've differentiated, we've put it equal to 0, we've got part of our coordinates. We know that we've got a coordinate 2 something and a coordinate 6 something. So what we have to do now is the next wee bit is we have to put them back into the original equation to get the y. So I'm going to do f of 2. So remember, I'm putting it back up into, I'm actually going to use the very original equation. It's easier to use than the expanded version because I can just work from the inside out. So f of 2 would be doing, if I look at the inside of the bracket, you've got 2 minus 6, which is minus 4. Minus 4 squared is 16. So you've got a 2 out the front. So you've got 2 times 16, which is 32. Then I'm going to do the same again for f of 6. So from the inside out, 6 minus 6 is 0. 0 squared is 0. So you end up with 6 times 0, which is 0. So my turning points are 2, 32 and 6, 0. So when I go to do my nature table, I go in numerical order. I go up to 2, up to 6 and then beyond. Now I'm just going to write down what my f dashed x was again because I need to move my screen up a wee bit. So I've got 3x squared, take away 24x plus 36. So that's quite a big one to substitute into. Right. So at this point, nature table, underneath your 2 and the 6, f dashed x is 0 because that's when your gradient's nothing. Choose numbers that are before the number 2. Now you could simply choose 1 or you could choose 0. 0 is a much easier one to sub in. Between the 2 and the 6, I'll probably just go with 3. And then after the 6, I'm not a big fan of trying to sub in the number 7. You can going to use number 10, right? Because 10 is really easy to sub in. So what I'm doing here is if I put in f of 0, so f dash 0 would just give me 0, take away 0 plus 36, which is a positive number, so we put a positive. If I sub in the number 3, remember that all this working here in this red pen is optional. It doesn't necessarily need to be there. It's just showing you what I'm doing. A lot of people do this little bit in their head. Right, 3 squared is 9. 3 times 9 is 27. So the first bit's 37. 24 times 3 is negative 72. And then we add on 36. Well, 27 and 36 isn't quite 72 anyway. It's 50, 63. Take away 72, that's negative. Don't need the number. I just need to know it's a negative. And then if I plug in the number 10, so f dashed of 10 is, well, 10 squared is 100, so that's 300. Take away 240, add 36. So that's clearly going to be a positive number, so this is positive. So my shape is up, along, down, along, up. So at the 2, we've got this lovely maximum turning point shape. So 232, we say, is a maximum turning point. And at the 6, 0, we've got the minimum shape, so we say that is a minimum turning point. And that there is what we are after. As our conclusion, that is us got the turning points and the nature. So thanks very much. I hope this has helped. I think I've got a third example. Here's one that I pulled from 2019 paper 1 question 1. Now watch the word in this one. It just asks you for the x coordinate. So very quickly work through this one. So this one is in terms of y. So for this one we do dy by dx. Now, a half times 4 is just 2, so this gives you 2x cubed. 2x cubed becomes 6x squared. And when you differentiate the 6, it just disappears. Now, for stationary values this time, we're going to set dy by dx equal to 0. So no f of x's in this one. So we then do 2x cubed minus 6x squared equals 0. That gives you a common factor of 2x squared. Remember, you take out the highest power possible, leaving you with x minus 6. Well, if 2x squared is 0, then x must be 0. And this one gives you x equals 6. And remember, that gives, we know a coordinate is 0 something and 6 something. But I've actually just realised something. I've gone too far. The question only asked for the x coordinates, and I even mentioned that at the beginning. And the thing that's just struck me is this is a paper one, and if I was to go find the y coordinates, I'd be having to do 6 to the power 4, which is like 1200 and something. That's too big. Non-calculated, that's not possible. So actually, if I just rub out that, this question was done here. It just wanted the x coordinates. So the x coordinates were x is 0 and x is 6. So that was just a wee short twist on a question. And it's just taught me always read the question. So hopefully this has helped. If you had the TJ Higher book, these are certain questions that I would ask my pupils to go try now to get lots of nice practice with this. Thank you very much. Bye-bye.